The brand new problem that we have to talk about is synthetic problems, synthesis. How do you make this thing from whatever constraints you have? Frequently, these are in the context of, I want you to make one specific molecule from a list of relatively small constraints. Often, those problems are described by drawing a picture and you need to make this. Often, there's going to be an implicit nomenclature problem there as well. So if you see propyl T-butyl ether, you then need to interpret it as a propyl with a T-butyl on the far side and an oxygen joining those two. There's frequently constraints from alkyl halides 4 carbons or less, which are conditions or constraints. So you can't use alcohols unless you show how to make those alcohols from the halides. And I've described this before as being sort of a path that you could take, say if I wanted to fly from here to my brother down in San Diego. And these kind of conditions or constraints are essentially saying, hey, you need to start in upstate New York, which means that I have choices like fly out of Rochester, fly out of Syracuse, drive to Buffalo, fly out of Buffalo, visit my parents who live in Philly and fly from Philly instead. Or alternatively, like on a road trip path, when my parents come to visit me from Philadelphia, essentially, I ask them, hey, are you coming through Watkins Glen or Ithaca or through Syracuse? And so that kind of maps out the path that they're going to be taking to get here. And we're not going to discuss go on the throughway or Route 14. That's far too detailed for this kind of problem. All we're interested in here is the isolable intermediates. In other words, are you going through Syracuse? Are you going through Ithaca? Big blocks as opposed to the fine details. So the key thought here is going to be that you need to work backwards. And so you'll look at this molecule and you'll start to see ways in which you can disassemble it into smaller chunks, and that'll be the way to go. And so your primary tool for this is a retrosynthetic arrow. Retrosynthesis meaning in the backwards direction. But the other way you can think about it is, which of these bonds do I know how to make? And the reason why I'm saying which of those bonds is you, at this point, don't have the toolkit necessary to make carbon-carbon bonds. So in other words, the only bonds in here that you can make are those carbon-oxygen bonds. And since this is much bigger than 4 carbons or less, you're going to have to divide the molecule into halves, more or less, if you can. And so really the choices you have are, can you do this blue disconnection or can you do this red one? So let's talk about the blue one first. You could imagine this coming from a SN1 type reaction wherein the propanol is being used to react with, say, a tert-butyl chloride. And if you were to mix those two together, you could imagine how you could do an SN1 and then this would end up embedding and that would give you the final products. And so you're really focusing on a potential SN1-like process there. However, there's a problem with that thought, and that is that this propanol is itself not one of the constrained options that you had originally. It is not an alkyl halide. In other words, we have to decide where the propanol can come from. But of course, I would hope that you could recognize that propanol could come from some propyl, say, iodide or chloride or bromide, and that would be an SN2-like process. And again, the choice of the halide is not important. That's kind of the Rochester versus Syracuse versus Buffalo, which airport do I fly out of choice. But they're all roughly equivalent. They are some version of a propyl halide. So anyway, if we're going to work this through in a forward direction, I would then show you how to combine those, and that would be the answer to this question. But this isn't the only path, and this is kind of my point about the road trip path or the flight itinerary. There are multiple ways to get to where you want to go. One of them was to run an SN1 type path first, but you could instead choose to run more of an SN2 type path, and that's this red disconnection right there. You could imagine that if you had, say, a propyl iodide, that you could run a reaction that involved some kind of SN2 type process with propyl iodide, but using the tert-butyl alcohol, especially if you converted the tert-butyl alcohol into a better nucleophile. Of course, the problem with that thought is, again, that the alcohol is not fitting our original constraints, so this would have to come from, say, tert-butyl chloride via some kind of SN1 type process. And so the core answer to our question is going to be an SN1 and an SN2 in some order, but you need to combine both in order to end up at this desired product. So now, once you've done the retrosynthetic analysis, you are ready to move in the forward direction. And in fact, a good answer in a synthetic problem is going to involve both. I want to see your disconnection process. You'll receive partial credit from doing the retrosynthetic analysis, but to get full credit, you will then need it to stitch together in a plausible forward direction as well. So first you do the disconnection part, and then you start building the forward direction synthesis. So if you're looking at this blue, where we're actually fundamentally starting is with propyl iodide. And since this is one of our perfectly valid starting materials based on the initial constraint of an alkyl halide, 4 carbons or less, then it's just a matter of deciding what conditions will lead to the desired outcome. And here I would hope you would choose some good nucleophile, like say sodium hydroxide, in the presence of some SN2 biasing solvents like DMSO, and that will go ahead and provide your desired primary alcohol, which you can then use in the next step. And then you can take the tert-butyl chloride chloride and simply dissolve that up in some propanol, and that might very well do an SN1 type reaction on its own to give you the desired material. But you could speed things along if you wanted with a trick that we picked up from the lab where you add in silver nitrate or something of that variety to cause the chloride to precipitate out. And so this will help pull the chloride off and speed up the process for an SN1 reaction. Although your full answer would be 100% correct without the silver nitrate. This should run an SN1 reaction on its own to give you the final product. And this would be a perfectly acceptable answer if this was your retrosynthetic analysis in the first place. If instead you started going through an SN1-like process with the tert-butyl chloride, then we essentially reverse those ideas. You start with the tert-butyl chloride. You would want this to essentially become tert-butyl alcohol, which means using water as the solvent, and that will lead to the desired product. But of course, you can speed things along a bit more quickly if you use silver nitrate to remove the chloride and so on. And once you have the desired tert-butyl alcohol, then you would need to conduct a Williamson ether synthesis, which basically involves using a relatively strong base, and sodium hydride would be an excellent choice here, in order to then go ahead and run the follow-on reaction with the propyl iodide. And you would probably want to run that in, say, DMSO, again, a good SN2-like solvent, to give rise to your desired product. And so the idea here would be that you would take your tert-butyl alcohol and you would add to it sodium hydride, and you would basically let that stir in some solvent for a while until the bubbling stopped, because what it's doing is generating hydrogen gas and making your O-. You don't draw that O- anywhere in here because it's not an isolable intermediate. You cannot isolate the O- material easily. So instead what you do is you just simply throw these two starting materials together, you allow it to form the O- in the first place, and once you're pretty sure that the O- is in there, then you throw in the propyl iodide and it stays in the same flask. So both of these two steps happen in the same flask. So step one is in one round bottom flask, and then you just simply add propyl iodide to that, and then eventually you isolate it, and there's your final material. This would be a fully correct answer for the SN1 followed by SN2 process. And in both cases, again, the silver nitrate is an added thing that you wouldn't necessarily need to include. This should perform an SN1 reaction on its own. And likewise here, if you were to go ahead and draw out the O-, that wouldn't be wrong exactly. It's just not one of the isolable intermediates. So you don't need to draw it. If you did, it isn't wrong, but you don't need to draw it. This is all you would need in order for it to be a fully complete answer.